Hi guys, happy Monday. Here we are again, but this time from sunny Plattsburgh. I hope you are healthy and safe. And we're gonna have one more video for this week. We're actually 5 weeks out of the finals week, so we're getting there. Time will go by fast. Please try to take advantage of everything that you can from this course and come out better, right? So for today, I'm going to start again by giving you a little bit of feedback concerning LO16 and LO17, and then I'm going to cover chapters 18 and 19, which means we have LO 18 and 19 until Sunday 11:59, just right before midnight. All right, so from LO 16, the only item that looked a little bit tricky to the majority of you is the question if we should exclude data collected in error from data analysis. And if something is collected in error and we cannot recollect it, and we do know for sure it's wrong, then it shouldn't be included. You should exclude it. And if you go to page 228 and you see table 16.1, the example, you will understand that. But if you really think about it, it's not that we're taking out data that we don't like. They're wrong data. They're data that are not representing true values. Okay, so if they are including the analysis, they will just throw us off. Do we really want that? Okay. Other than that, everything looked great, and I'm happy with your performance. LO17, again, very happy with your performance. One item, again, we're talking about drawback of electronic recording. Okay, which one is not a drawback? When we have automatic electronic recording, which means I send you a link and you go online and you submit your answers, there's no, there shouldn't be a way to have you submitting your answers twice because you receive an individualized link, right? It could happen, but that is what's going on with LO17. I don't think it's really hard. It was a little bit confusing, the wording, but that's about it. Let's move to what we have today. We have a lot of material again, pretty exciting stuff, and stuff that you could definitely use towards your final project, right? All right, so chapter 18, statistical approaches to data analysis. There are qualitative data, there are quantitative data, next science and exercise science. Next, we mainly have quantitative, mainly, not just quantitative, but mainly. If we try to break that down a little bit more, we have observational data. When we don't manipulate, we just observe a phenomenon, and then we can have correlations. And then also we have experimental data. When there is manipulation, then we can have causation. In any case, both of them, the analysis, the underlying analysis, is under the same philosophy. Okay. Now we've talked about the types of data, nominal, ordinal, interval, and ratio. I'm not going to cover that again, but going over the chapter, you can refresh your memory. When we talk about frequency of distribution, we always talk about randomized. Randomness will most likely give us a normal distribution, and if you see it as a graph, it would be a symmetrical graph. Right? We usually like that, or we assume that happens, or we check for normality of data through statistics. Now we have the descriptive statistics and we have inferential statistics. Most of the time, in most papers that you see, we start with descriptive statistics. Okay, so we have we say that we look for the central tendency. We have the mean, the mode, and the median, and then we have the variability that leads us to variance, that leads us to standard deviation. So, for example, classic example is in total 365 participants agreed to participate. Parenthesis mean age 20.5, standard deviation 2.6. And that's a way to show through descriptive statistics specific characteristic of your demographics, okay, which is age, BMI, height, could be something like that. Inferential statistics. Now, inferential statistics, we can make a generalization from the sample to the population. We'll have to be really careful there. A lot of times there's error, we call it standard error, and it's the difference between the estimate that we have from our sample with the population that we're trying to generalize, extrapolate. Now, let's talk about the null hypothesis significance test, right? We usually we say the null hypothesis is a no relationship between the dependent and the independent variable. And then there is another hypothesis which we call alternate hypothesis, right? But there is a relationship. And those two hypotheses are mutually exclusive. So if one is there's evidence for one, then we have to reject the other one. We can accept both of them. In general, we design it in a way that we're trying to reject the null hypothesis, that there's no relationship. But in order to do that, we'll calculate a value. We call it p-value. That is the probability that the data we have show that null hypothesis is true. So we put a value. Usually it's 0.05, the p-value, right? A lot of times, especially if you use one of the popular statistical software. By the way, you can change it up, and then we compare it to another level, right? So we have an alpha value. So we have the alpha value, and if we set the alpha value at 0.5 and we found a p-value that is less than or equal to alpha, then we reject the hypothesis, the null hypothesis, which means there is a relationship between the dependent and the independent variable. If the p-value is larger than alpha, that we set it at 0.05, let's say as an example, then we accept the null hypothesis, which is that there is no relationship between the dependent and the independent variable. Now here, I'm sure you've heard about that before. We have type 1 error, which means the null hypothesis, also called HO, shouldn't have been rejected. And then I have type 2 error, the null hypothesis should have been accepted. So errors happen. But in general, we're trying to see if something is significant. So if, again, p is less than or equal than alpha, we reject the null hypothesis, which means that there is a significant relationship, or there's a relationship that is statistically significant between the dependent and the independent variable. But significance does not mean importance, does not equal importance. So that's why we talk about the effect size. Before I go to the effect size, I want to talk about the statistical power, which is the ability of a test to actually detect whatever we're looking for, that effect. Okay, so we'll talk about power a little bit later. So whatever test we did, maybe it found that it's significant, but it's not powerful enough to detect or not detect. And we want to have a test that's really powerful. And the best and the simplest way to do it, and the one that will have a huge effect on the power, is increase sample size. We'll talk about other ways to do it in a little bit. That's power. Let me go back to the effect size. As I said, significance doesn't mean importance. So something is significant, but doesn't necessarily mean that it should be important. Okay, so we found it significant. Is it important? Then, in order to answer that question, we have to look for the effect size. So usually, classic example is Cohen's D. D 0.2 is small, 0.5 is medium effect, and larger than 0.8 is large effect. Of course, we're looking for large effect, obviously. Confidence intervals, the range of values, as the book says, within which we are confident that the population value lies. And it has a direct relationship to the alpha value, or the p-value, whatever you want to call it. So if we have an alpha value, we say that 0.05, the confidence interval is 95%. Okay, so we usually put it in there. All right, let's go to the analysis. Analysis of variance and the regression analysis. They're based on the general linear model, GLM. If you take any stats or advanced stats, we'll talk about that. And we are usually comparing means. And in order to compare means, we'll have ANOVA or t-test, and we're going to explain a little bit. When we have multiple measurements of the same thing, we say we have repeated measures. It's more than two. But when we're comparing means, I can compare my mean now to my mean in 2 weeks, so that would be within subject. And then we'll compare my mean to your mean, and that would be between subjects. So we'll have two groups. So it's a different analysis. Now, if we have two means, either two measures like me now and me after intervention, or two just groups, then we'll do a t-test. Okay, that's a t-test. Nothing too sexy here, as I always say in class. It's just two means, it's a t-test. If it's between subject, we call it independent t-test. If it's within subject, we call it dependent t-test. So if you see dependent t-test, you know you have two and it's within subjects, like me, there's intervention, for example, and then it's just again me, my me. Now, three or more, then we go to ANOVA. So t-test, what is it? It's an ANOVA with two means. Three or more, we go ANOVA, right? And then again, it can be in between or within. There we get an F statistic which is similar to the p-value, and then that's how can you figure out, and then that's how we can test the hypothesis through the F statistic. So if you ever, let's say, use SPSS and you do an ANOVA, excuse me, the F statistic will help you test the hypothesis. Again, here, if the null hypothesis is rejected, which means there is a relationship between the independent and the dependent variable, that we mostly likely want this to happen, there are some things that even in SPSS they call post hoc tests or post hoc analysis, and then we're trying to figure out which ones how much, and so on and so forth. Just try to go a little bit deeper. All right. Now, are there any more complex? Yeah. What if we have more than one dependent or independent variable? What's going to happen when we have three independent variables? Okay, not just one. There we can do a main effect analysis. Well, the main effect is we see how one independent variable separately than the other one affects the dependent, so separately. So we have some athletes and we are interested in how much they sleep and how much caffeine they take, and then the dependent variable is their performance in something, let's say 5K. We see how sleep affects 5K, and we see how caffeine intake affects 5K. That's the main effect. But we can also do factorial ANOVA that shows what's going on with interaction, what's going on with the sleep and caffeine together towards the dependent variable, which was 5K. And there's a great example in our book. You can see figure 18.1, and it shows exactly that when we have two independent. Now let's talk a little bit about correlation and regression. ANOVA usually we do with nominal type of data, interval ratio regression. Okay. Now we talked about Pearson correlation before. That's R. It goes from -1 to 1. That would be perfectly negative correlation, perfectly positive correlation. 0 means no correlation. There's no relationship between the two variables. If R is not 0, so if there's any kind of relationship, of course, we can test for the significance. Here, the coin is deep, 0.1 small, 0.3 medium, 0.5 large. R squared has to do with regression, okay? Mostly we'll see it in regression, and then there, R squared shows how much of the variability depends on the independent variables that we have. So we may try again to see caffeine, sleep, gender, age, BMI, and all these factors, how they affect the 5K race. Right? All these factors, how much can we say that they affect the variability of the dependent? If the R squared is 0.69, that means 69%. We want this to be as high as possible, which means with whatever variables we chose here to figure out what's going on with that 5K, which is our dependent, right? We pick the ones that actually affected the most, or the combination of all those affected the most. So we pick the ones, and that's how you do regression analysis, and you have regression models, and you can predict. All right. in our book, there's a bench press example that can help you figure out more. Here we have error, which is called residual, SEE, and that's a way to assess the regression equation that we can have. And regression equations are great, and we can have more than one variable that will give you multiple regressions, which means multiple regression models, which means more sophisticated regression equations. But again, regression equation has been created in essence to be able to predict. Okay, so you create those models and you try to predict that independent variable, whatever it is, based on all these independent variables. Okay. Sample size, and again, another thing about your paper, right? You're going to tell me that you want to do something with 10 people. Why 10? Why not 9? Why not 11? How did you figure that out? One way to go around it is to know that you're looking for power, right? But you can't be overpowered. You can, if you need 10, you can ask for 15 because then you're using 5 more participants for no reason. The IRB will not accept that. If you need 10, you can ask for 8 because then you're underpowered. So you have to be around 10. You can say 12 because I may lose 2. So due to retention reasons, I asked. We did a power analysis, we got 10, but we're going to try to recruit 12. That's perfect, acceptable, right? Now we have to, in order to figure out the sample size, we determine the smallest effect that would be desired to detect, and that's for you. When you do your paper, you determine the alpha level and then the desired power, 0.8, that's classic, right? And there's a specific software in the book that's free, and you can use it, all right, to figure that out. All right, so from this chapter, descriptive statistics, inferential statistics, p-value, effect size, confidence intervals, and then t-test, ANOVA, and regression. I want you to know those things because it not only it helps us understand stats, but you see, you read a paper now, I want you to be able to understand more. Okay, of course we just scratch the surface, but at least the information that I cover, I would like you to be familiar with. All right? All right. Chapter 19, drawing inferences or logical fallacies. Very important. We see it all the time around us, and it's really crucial to be able to know how you go from A to B, and that makes sense. Okay? And your B is not a fallacy, but is a correct inference, a valid one, as we would say. All right. Inference. I want you to know that word because we use it a lot in papers like our results infer or inferences of our results. That's really scientific and nice language to use. Now, an inference is when we have draw a logical conclusion from something that I know. Sounds simple. We'll see how simple it is. Through technology, there's an abundance of information traveling left and right, and we have access to that information. But the speed of information doesn't mean that I draw logical conclusions, right? You see what's happening right now. That's relevant, kind of. So you see what happens right now with COVID, right? You read a lot of things. Do you think they're valid inferences or logical fallacies? Something to think about. All right. What's the scientific process? All right, let's talk about what's the scientific argument and what is logical reasoning. Now, in the base of everything, we're trying to avoid those fallacies and we're trying to avoid making the wrong conclusions. We have 2 examples in figure 19.1. Are they valid or invalid? Read about them, think first, and then read the next of the chapter to see the right answer, to find the right answer. Types of inferences. Let's see. As I said before, making some kind of inference easy. Making the correct one, not so easy all the time. 3 groups of reasoning. So we have different types of inferences. We'll start with Aristotle, right? Deductive reasoning. If you have taken a philosophy class or in the stats 101, I'm pretty sure you've heard about that before, that from the general you go to specific, right? Of course, that information has to be checked for soundness and validity, but that's the main idea behind deductive reasoning. Now, forms of deductive reasoning. We have the law of detachment, It's simple. We have one conditional statement. We have the law of syllogism. It's complex. We have two conditional statements, and then we have the law of contrapositives. Okay, one hypothesis, one conclusion. In general, in our book, we have a lot of examples that you can go and review. I'm not going to go one by one right now, but those are the three forms of deductive reasoning. In any case, the conclusion is rejected if the reasoning is invalid or one premise is false, at least one. Inductive reasoning. So here we have Sir Bacon. We go from specific to general. In order to go from specific to general, you have to have an abundance of information and a lot of pieces that when you put them together, you can make come to a conclusion for something more general, right? This is the basis of scientific method, right? You do something with women, I do something with men. Somebody does adolescents, somebody does African Americans, somebody does Asian Pacific Islanders, and we all do the same subject. And at some point, we collect all the information, and maybe we come to a conclusion for the whole population. I don't know, but that's the idea, right? Here, and there's a subcategory here, the abductive reasoning from Peirce, which is the best explanation we can have, that from an observation we move to a hypothesis. All right, reasoning. In scientific research, which types do we use, and within a manuscript, within a paper, where do we find them? So deductive would be in the conclusion, because we have our results, and then we have past results, and then we can go from something general to something specific. Inductive usually is in the intro, and it helps us form a hypothesis of what is already known. Right? Several examples in the text. Now, logical disagreements. Do we all agree in science about everything? Heck no. You will see scientists and well-established scientists. For example, hydration, dehydration is classic. There are two schools of thought fighting against each other. Sports neuroscience, is FNIRS better than EEG? We just go against each other. We see from our perspective, but it's not necessarily negative. It just pushes for more and more and more research until we found that one truth, if there is one truth. Okay. Logical fallacies. Any argument, any inference we make, and you see them at the end of the paper, in the conclusion, after the results, it's not to be touched, and it's not perfect until the end of time. It is, hopefully, best case scenario, the best inference we could make, the best conclusion we could make, the most valid conclusion we could come to, based on the information we knew at that point. So there are a lot of things that we thought that were true 20 years ago, 10 years ago, 5 years ago, and now we're like, nah, bro. No. Because based on new data, that theory cannot stand anymore. Okay? We have formal fallacies from deductive reasoning, not very common, and we have informal fallacies, which is from inductive reasoning, which they are more common. We have the relevance one. So we have an inference which is irrelevant to the conclusion, very popular. Another popular is presumption, unsupported by the inference, unsupported inference. And then ambiguity is not that it's rare, because it uses, for example, vague terminology, and that's how we end up with a fallacy. Now, methods for reducing logical fallacies. The book gives us a lot. Of course, the scientific community in general, direction we go in order to avoid that is through peer review. Okay, your peers are reviewing your work. Right. But in general, what we can do, we have 6 guidelines from the book. Premises based on truth and relevant information. Makes sense. Conclusion is based on those premises. I hope also makes sense. The issue is addressed by the premise and not something else. Premise and conclusion are applicable to the issue. No broad claims. Oh, I hate that. Don't make any bold statements. Okay? Keep it airtight. Whatever you investigated, don't try to generalize to everything. Just try to keep it there. Like, don't do any bold statements. If you do bold statement, make sure you have the evidence to do that. Okay, a lot of people do that. And line of thought, there are a lot of examples in the book. You can't just jump from one idea to the other. You have to have a train of thought. So there's like, for me, we know A, we know B, we know C, we know D, we know E. Good. We don't know this, therefore it has to have a flow. I have to be able to understand. Okay. For example, when you give me the purpose of your research, if I'm like, how did that come up? Why is he talking? Is she talking about female student athletes now? Right? There has to be some kind of an approach that will lead me to that question. If I, as I'm reading your intro and I'm going all the way to the purpose of your research, of your proposal, I should be expecting it before reading it. If I read, I'm like, what? How did that? It doesn't make sense, right? So make sure there's flow, please. That's for your paper as well. Guidelines for fighting and eliminating our own fallacies, right? You try to disagree. I do it all the time, trying to see what would the reviewer say? What would the reviewer say? So I'm trying to keep it really airtight and not expand it. Just make sure it's as safe as possible. Never happens, but I'm trying. You have to have evidence for whatever main points you have. Okay, you have to identify your own tendencies, right? Let's say you generalize, you do a correlational study, and you always talk about causation. No, you know that. Don't go there. Just correlation. Correlation. That was it. Okay. Uh, as I said before, if you do broad claims, make sure you have a lot of evidence to support it. Otherwise, any reviewer will just destroy you, and they should, because it's a logical fallacy. You can't just say that, right? And know your audience. Make the appropriate premises and appropriate inferences for them to understand them and to help them be better theorists or practitioners. Okay, so from this chapter, make sure you understand what's an inference, how we create a valid inference or invalid, and how we can avoid the logical fallacies. Okay, there are different school of thoughts. All of them, though, should lead us to make arguments that are valid based on what we know at that time. Okay, so again, try to keep it tight, especially for your project, let's say, or when you read a paper, when you write a paper tomorrow. Come to conclusions that you can really justify based on whatever you presented before and what others presented, and then you combine all that information. Glossary is really helpful if you want to go there. I hope you're okay. I hope you're good. Let me know if you need anything. I hope you're having a great week. And again, although you have to stay at home and you should lift intentionally, not habitually. Bye, guys.